All right. Good morning, everybody. Let's come back to our lecture today. Um, Now, in the previous lecture, we discussed about angular momentum, right? We define the angular momentum for a single particle, and then we extend our discussion to a system of particle. And for system of particle, the angular momentum about a certain axis can be written as the moment of inertia about that axis multiplied by the angular velocity of that system. Now, this is actually applicable to a system with uh, in the form of a rigid body, where you have a well-defined angular velocity for every particles. Okay, so so in that case, we can calculate the angular momentum for a system of particle, and then we talk about equilibrium. Okay, in your high school study, you learn about equilibrium. In that sense, if a body is not in motion, then the total that means the total momentum of that body is zero, and that means the total net force acting on that body is zero. Now we have another condition for equilibrium. This condition you might have learned in high school is that instead of just for the translational motion equilibrium, you also have rotational motion in equilibrium. So for rotation, for a body that does not rotate, the total angular momentum is zero, right? So the net torque acting on that body, because the net torque is the rate of change of the total angular momentum. So if the angular momentum is zero, the net torque acting on that body is also zero. And so these are the cool conditions for equilibrium. Now we discuss a simple example of equilibrium. Now this is in fact a simple example of moment of force you learn in high school. Now we have a brief review of it. Okay. Now suppose we have a uniform rod of length L and mass M, and the rod leans stably at a certain angle theta. Theta is the angle that the rod makes with the vertical direction to the vertical direction, and it leans on the wall. The wall is smooth, so this part, the upper end of the rod, does not experience any friction. But the lower end of the rod lies on the ground, and the ground is rough. Okay, so it has a friction here. Okay, so there's a frictional force pointing towards the corner, the junction between the wall and the ground. Okay, now so how to solve this problem? We want to find the maximum angle theta at which the leaning is stable. Okay, and we are given that the coefficient of friction between the rod and the ground is mu. So we are given this condition. We are given this parameter, and we want to find the largest value of theta for which the leaning is stable. Now we look at this force diagram. R is a normal reaction from the wall, and because we assume that the wall is smooth, so there's no frictional force. So the only force is the normal force. Now, whenever there is friction, there always is the tangential component of the force. But if we don't have friction, we don't have the tangential component. So you don't see a force that is tangential to the surface. And the forces must now be normal to the surface. That is the only force, which is the normal reaction. Okay. And for the point that is in contact with the ground, we also have another normal reaction, N. But now we also have a frictional force. The frictional force is, of course, pointing towards the wall, because that is needed for equilibrium. Okay, the rod tends to slide down like this, and so the frictional force must be pulling the rod back. Okay, so it must be in this direction. Now we study about the force equilibrium. Now we need two conditions. The first condition is the force equilibrium. The second condition is the torque equilibrium. So, but the force is two-dimensional here. So we have the horizontal component and the vertical component. For the horizontal component, we only have two horizontal force. The reaction force R here on the wall and the frictional force, and they must be equal because we only have two force. So in order for equilibrium to establish, we only the two force must be equal, right? Now the vertical force, we also only have two vertical force. The normal reaction from the ground and also the weight mg of the rod. And these must again be equal. Okay, so the balancing of the horizontal and vertical force simply give you two equations, two simple equations relating the force. Now we take moment about one point. We like to take moment about point P. That is the point the rod in contact with the ground. Because when we take moment about point P, the frictional force and the normal reactions they do not have any moment because the moment arm is zero here. So that means we eliminate these two forces in our equation, and that makes the calculation convenient. So that's why we take moment about this point. Now you can see the moment that is produced about P is due to the weight and the normal reaction R. For R, the perpendicular distance from the point P is L cosine theta. So we have R L cosine theta, right? The height here is the moment arm, right? So the height is L cosine theta. So it's R L cosine theta. And for the weights, okay, the distance from the point P is alpha 2. The perpendicular distance is here, which is alpha 2 sine theta. So we have mg, the weight, multiplied by the moment arm, which is alpha 2 sine theta. The two moments must balance each other because one is counterclockwise, the other is clockwise. So they must balance at the point P when we take a moment about point P. Okay. Now simplifying this equation give you the reaction force R. Okay. The L cancel and we can move the cosine to the right hand side, and that becomes 1/2 mg tangent theta. But as we know, R is equal to F. So the frictional force is also equal to 1/2 mg tangent theta, right? But I also know that in order for the equilibrium to occur, the frictional force must be smaller than the maximum friction. The maximum friction is equal to the coefficient of friction multiplied by the normal reaction force N. But N is equal to mg, so that must be equal to mu mg. So the condition for equilibrium is that the frictional force here given by 1/2 mg tangent theta must be smaller than the maximum friction that can be produced, that is mu mg. So we have this equation. This is the maximum friction that can be produced. It must be larger. It must be larger than the actual friction. Okay. Now this equation is simple. We just cancel the mg on both sides. We move the 2 to the mu side, and we take the arctangent. So that gives me the angle, the maximum angle. The maximum angle has to be smaller than arctangent of 2 mu. Okay, so simple enough. Okay. Now let's have a brief review about equilibrium for a solid. Now, suppose we have a cone like this. Okay. Now let's rest the cone with its base on the table. Okay, so that is the most stable equilibrium. That is your daily experience, right? When you put it like this, the cone is most stable. If you try to flip it, if you try to tilt it, you will find that if you tilt it by a little bit, the moment the center of mass will be raised. Okay, if you tip it about one side, then the center of mass will be raised. So that means this position is the minimum for the potential energy. If you raise, if you tilt the cone and its center of mass position is raised, then the potential energy is also raised, right? So the original position that corresponds to the position of the minimum energy. And so that is a stable equilibrium. Okay. When you tilt it, you can see the moment produced by the weights about the contact point will tend to move the cone back to its equilibrium position. So that is a stable equilibrium. Okay. Now, but it is not so. If you try to balance the cone with its vertex, if you invert the cone and try to balance it in vertex, you find that it is not stable. Why? Because when the center of mass, when the cone is slightly disturbed, you can see the position of the center of mass is lower, and so the energy, the potential energy is lower, also lower, and that means this position is the maximum for the potential energy. So that is unstable equilibrium. When you slightly tilt the cone, okay, you can see the torque produced by the weights at the center of mass will tend to topple over the cone. Okay, it will not restore the equilibrium position, but will move the cone further away from the equilibrium position, and eventually it will topple over. So that is unstable equilibrium. Now, how about resting the cone on its curved surface? If you tilt it slightly, if you move it slightly, you will find that the cone is now rolling around the vertex, right? And in that case, the center of mass position is neither raised or lowered. And the torque produced by the center of mass will not be restoring or disturbing the equilibrium. And that means it is a neutral equilibrium position. A neutral equilibrium means when you move the object by a little bit, the center of mass position doesn't change. Okay, so this is a neutral equilibrium. If you want to learn more about the center of mass, you may take a look at these e-learning modules. Okay, this is by Professor Kenneth Young. Now then, we will proceed to an important theorem in this lecture, that is the conservation of angular momentum. Now, when the net torque acting on the system is zero, okay, this is a total torque, okay? The total torque acting on the body is, or system of particles, is zero. That means because tau is equal to dl dt, right? That is Newton's second law of rotation. So if tau is equal to zero, then dl dt is equal to zero. And that means the angular momentum is a constant. Whenever you have the derivative of a quantity equal to zero, that means that quantity will not change in time. And that means that quantity is a constant. And for a body, you may write, rotating about a given axis, you may write the angular momentum as the moment of inertia multiplied by the angular speed. Okay, so that is the expression of angular momentum of the body rotating about a certain axis. Okay, now so that is the law of conservation of momentum. If the total external torque acting on the body is zero, then the angular momentum of the system is conserved. Now we have we emphasize that this law actually applies, although we haven't proved it. We just put the moment inertia into the derivative, right, in our derivation, but that is not valid actually. We haven't proved the general cases of conservation of angular momentum. Now, in fact, this is true. Even if the moment of inertia in this case is not a constant, the conservation of angular momentum still holds. Okay, so imagine a body that can be deformed. Okay, the shape of the body can change, and so I is changing. If I change to I prime without the present external torque, then omega will also change accordingly. Okay, because L is a constant, right? So if the O moment inertia and the O angular velocity is I and omega, the new moment of inertia and the new angular speed is I prime omega prime. The combination I prime omega prime is equal to the combination I omega. Okay, so the old angular momentum is equal to the new angular momentum. The angular momentum is conserved. Okay, so I can solve for the new angular momentum, new moment of angular velocity if I know the change in moment of inertia. If I know the OI and the new I can calculate the change in angular speed also. Okay. Now that finds a wide range of application. For example, a skater, right? When the skater rotates, you see the skater, when the skater rotates, he or she will contract his or her arms, right? And her legs, okay? So in that case, you can see the moment of inertia actually decrease because the distance of the particle, of the mass from the axis of rotation now decrease. By contracting her arms, the distance decrease, right? So if the distance decrease, the moment of inertia is summation MIRI square, right? So that means the moment of inertia also decreased. And by conservation of angular momentum equation that we have just derived, if you have a new angular momentum to be smaller than the old angular momentum, a new moment of inertia to be smaller than the old moment of inertia, you will have the angular speed increase. Okay, so the angular speed, because the I omega is constant, so I decrease means omega will increase. Okay. Now we also have another example of in astrophysics, and that's about neutron star. Now neutron star is a highly compact object. Neutron star is just about the size of Hong Kong Island, maybe 20 kilometer in diameter, about that size. But neutron star has the mass of the sun. Okay, you imagine the mass of the sun is now compressed to the size of a Hong Kong Island, and that is the density of neutron star. Now, because the star is highly compressed due to gravitational contraction, by conservation of angular momentum, its spinning speed will be increasing a lot. Okay, just like a contracting skater, but it contracts a lot actually because the sun is very large. When it compresses to a size of a Hong Kong Island, you imagine how many times of compression that has been made. So that's why a neutron star is spinning very rapidly. Initially, the star may spin a little bit, but when it's highly compressed, it will be spinning very rapidly. And the typical speed of rotation of a neutron star is several thousand revolutions per second. It is actually the fastest rotating object in the universe. Okay, so that is the picture of a rotating neutron star. Now let's give you a video to show you the skater. To show you how the skater
For decades, the Winter Olympic Games has drawn people from across the world to marvel at breathtaking athletics on the snow and ice. One of the most popular events is figure skating. Athletes meld acrobatics, dance, and physics into mesmerizing performances. It is the sheer precision that separates the skilled athlete from the novice. Through years of tireless training, skaters must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
Okay, is that clear? So very simple illustration of the contraction when the arm contract is spinning very rapidly. Okay, now this is the demonstration you commonly seen in the lecture hall. Although I cannot show you now because due to the pandemic we cannot have a face-to-face lecture. But that is like a common demonstration. Actually, I have shown you a similar demonstration when we play around with Xiu Fei in the demonstration that I show you in the video in the previous lecture. Now, Doraemon has interesting things that are called Zhuqingting. Okay, it said that you put the Zhuqingting at the top of your head, then it's just like the blade of a helicopter. So when it's spinning rapidly, it can lift up your body, and you can fly in the sky. Now, but this is not possible actually. Now, imagine if you consider Doraemon and his Zhuqingting as an isolated system in air. If now the Zhuqingting is spinning faster and faster, then by conservation of angular momentum, Doraemon's body will spin in the opposite direction. Because initially, the Zhuqingting does not spin, right? So it has zero angular momentum. So when it spins, when its spinning speed is accelerating, that means the angular momentum of the Zhuqingting is increasing. So in order to preserve the total angular momentum to be constant, Doraemon's body must be rotating in the opposite direction in order to counteract the increase in angular momentum, right? Yeah, just like a helicopter. So in that case, that means that Doraemon's body should rotate in the opposite direction, and it will break his neck. Okay, so that is not possible. Even if you have a very big Zhuqingting, that is not possible. Now, how do helicopters cope with that? Helicopter has a rail rotor, and the rail rotor actually produces a torque to counterbalance this effect. Okay, if your blades rotate in an accelerated manner, then the body of the helicopter will tend to rotate in the opposite direction. But the rail rotor is able to produce a torque that balances that extra rotation, and that makes the helicopter stable. Okay, now some helicopter maybe have two sets of blades, and they rotate in opposite direction. So the angular momentum can always be conserved without making the body of the helicopter setting it into rotation. Okay. So this is a common design in the toys, in the remote control toys helicopter. Okay, you have two sets of blades rotating in opposite direction. Now let's have a example on conservation of angular momentum. Suppose you have a merry-go-round like this. Okay, the merry-go-round is we assume it to be a uniform disk of radius r and mass m, radius capital R, and it's rotate with a constant angular velocity at the beginning. So you have a boy at the rim of the merry-go-round, and the boy slowly rocks towards the center, and eventually the boy comes to a distance of r/2 from the center of the merry-go-round. So my question is, how would the angular speed of the boy and also the merry-go-round as a whole, how would that change when the boys walk inside? Okay. Now we can calculate the initial moment of inertia. The initial moment of inertia is the moment of inertia of the disk, which is half mr squared, big M, big R squared. Okay, plus the moment of inertia of a boy, because we can treat the boy as a point mass. Okay, so its distance from the center is capital R, so its moment of inertia is just mr squared. So the two terms add together to give the initial total moment of inertia. How about the final moment of inertia? This doesn't change. It still has the moment of inertia of half mr squared, but now the boy has walked in is now at a distance r/2 from the center. So the boy's contribution to the moment of inertia has changed, and the new moment of inertia due to the boy is mr/2 squared. So that results in the new moment of inertia. And by conservation of angular momentum, the new angular speed is I/I prime multiplied by the old angular velocity. And so we substitute these two values into the equation, and that gives you the result. Okay. Now this is another example. This example is slightly more complicated because it involves a small piece of precedent. Okay. You imagine now you have a small piece of precedent of mass m, initially flying with a velocity v, and it is eventually attached to one end of a rod, which is hinged at its center. So the rod is able to rotate freely about the center. Okay. And the rod, this is the top wheel, so the rod is in the horizontal direction. So you can neglect gravity, and the mass now stick to one end of the rod and set it into rotation. So eventually, the rod and the piece of Patterson, they rotate together with a certain angular velocity, and you are required to calculate that angular velocity. Okay. Now, first we have to remember what is the moment of angular momentum for a point mass. Okay. Now the answer is easy because if you remember our introduction about moment of inertia, you may have memorized. You may have remember how do we define L for a single particle? It's the perpendicular component of the linear momentum multiplied by r, right? Now the velocity has a direction. The momentum is mv, right? But the momentum, the linear momentum, is in a direction that is perpendicular to the rod. So the perpendicular component of the momentum is actually the momentum itself because it's only has the perpendicular component, right? So that means we can have mv multiplied by this distance r. And here the distance r from the pivot point is alpha 2. So we simply have mv multiplied by alpha 2. That is the angular momentum for a single particle about the axis of rotation. Now the final total angular momentum is I omega, but angular momentum is conserved in this case. Now, how to calculate the moment of inertia of the composite body? Well, for this particle, the moment of inertia is, of course, the mass m, small m, multiplied by the distance from the pivot, which is alpha 2 square. So small m alpha 2 square. And for the rod, for uniform rod, about the center, the moment of inertia is 1/12 over ml, 1/12 ml square. Now we already have calculated in a previous discussion, so we don't repeat it. Okay, this is the moment of inertia of uniform rod about the center. So the sum of the two terms gives you the total moment of inertia, and you've applied the conservation of angular momentum. The final angular momentum equal to the initial momentum, right? So you got the angular speed as this. Okay, so that is again a simple example. Now, let us have another example. I let you do it. Okay, suppose you have a uniform disk, and the uniform disk with mass m, capital M, and radius capital R is rotating with angular speed of omega naught. Now we have a uniform rod. The uniform rod has a length of 2r. So the uniform rod has exactly the diameter, has a length that is equal to the diameter of the disk. And the rod is now has a length 2r, and the mass small m is released gently at the diameter of the disk. So eventually, because of frictional force between the rod and the disk and the rod eventually rotate together, okay, with a common angular velocity. So now you are required to find out that common angular velocity. Now, initially, the rod do not have any rotation. It simply is released gently onto the disk, but with its length along the diameter. Okay, and eventually the two rotate together with a common angular velocity. So you are now required to find out that angular velocity. Okay, now these are the value of the beta. The angular moment of inertia is beta mr square for uniform disk and also for rod. So please use a few minutes to work it out. Okay, please take out a piece of paper and you try to write down the final total moment of inertia of the rod together with the disk. Okay, and you apply the conservation of angular momentum. Anybody know how to do it? Any response from you? Uh, 6/7 omega naught. It's not that simple because you have two mass here. The small mass m of the rod is not the same as the big mass capital M of the disk. So you got two parameters of the mass, not just one mass. Can you modify the equation a little bit? Anybody who found the answer? And also you have to use the beta, right? The beta for rod and the disk they're not the same. Anybody who got the result? I think your answer is correct. Okay, let's do it together. Now, initially, the moment of inertia is only the disk, right? The rod is not rotating, so we only have a half mr square. Is that right? So the initial angular momentum is I initially have omega naught, right? So this is the initial angular momentum. How about the final angular momentum? I call it I prime. This term is still there because this is always there, right? But now we also have the rod. For the rod, the moment of inertia about the center is 1/12 multiplied by the mass of the rod. The mass of the rod is small m. And the length of the rod, now notice that the length of the rod is not L. It's now equal to the diameter of the disk. The diameter of this is 2r. So you have 2r squared here because this is the diameter. Now this is the length of the rod, right? And so you have 1/2 here of m plus what? This is 4, and you have 1/3 left. You are left with 1/3. Okay, small m, and you pick out a common factor of r squared here. Is that right? And the new angular speed is omega prime. Okay, so now by conservation of angular momentum, we got the new angular speed as the I over I prime multiplied by omega, right? I prime is this. I prime is this guy. I is this guy, right? So now we cancel the we write the rod here, and so eventually we got m over m plus 2 over 3 m. Is that right? Omega naught. That is the answer. Okay. All right. Any questions about this? Now this is just for fun. Okay. Have you seen a cat falling from a great height? The cat is able to turn his body, right? In the mid-air, the cat is turning his body, so it's able to land with his 4 feet facing the ground, and that increases chance of survival. If his lands not for the 4 legs facing the ground, then he may have a high chance of getting injury. But it somehow can turn his body such that when it lands, it has 4 hands, 4 legs facing the ground. That is a kind of a trick played by the cat in rotating his body. Now, how does the cat do that? Okay, the idea is like this. The cat is not a rigid body. He can contract his arm, leg, to decrease or increase the moment of inertia. So what he does is that he first retract the front body, retract his arm. So the moment of inertia of a front part of a body is decreased. Okay, and that makes the front part rotate faster. So he turns the front part of his body first. And by conservation of angular momentum, his rear part will rotate in opposite direction. But he actually will extend his rear part. So that makes that turn slower. Okay, so he turned the front part faster, and it makes the rear part to rotate in the opposite direction slower. And after he turns his front part, he extends his forearm. So it lower the front part rotation, right? And he retracts his leg, so it speeds up the rotation of his rear part, and that makes the rear part to turn again. Okay, and eventually he managed to turn his whole body facing with the 4 legs facing the ground. So that is an interesting trick. Now let's see the video of a cat rotating his body. Let's see it again. Okay, retract his front leg, so it's turn his front body. The negative rotation on the other side, but then he extend the front leg and retract his lower body, so it makes the turn complete. Okay. And angular momentum is conserved in this situation. So it's quite interesting to see that, right? Now, and we also have an other example. This is a joke, okay? The cat can fall from a great height. Okay, so this cat asked the old cat, how many lives have you lost? He said he lost 8 lives. Now, so there's a legend who say that cats have 9 lives because cats can fall from great heights without getting injury. So that's why people say cats have 9 lives. Now, the trick that play with the cats is like this. Now, if you take a look at the falling heights, if a human body fall from a height of about 6 and 7 story high, then his chance of mortality rate, the chance of getting die is almost about 100%. But if you look at the cats, then the chance of dying is actually much smaller. Now, of course, when a cat falls from great height, it gets injury. This is a cat injury rate given by some statistic. But you can see, even though it gets injury, it will not that will not be fatal. Now, why is it that? And when people find that the greatest rate of injury happens at about 6 or 7 story high for cats. If you go beyond that, the injury rate actually is falling. Now, the trick is that the secret for this is that about 6 or 7 story high, the cat falls after falling these heights will be almost in the terminal velocity. The terminal velocity of a cat is actually much smaller than human because a cat has a smaller mass. So it has a smaller terminal velocity. And after falling 6 and 7 story high, it reaches terminal speed. And after it reaches terminal speed, the net force acting on this body is almost 0. And therefore, when it reaches terminal speed, then the net force is 0. The cat feels relaxed. And it has more time to turn its body. So it turns its body and has its 4 legs facing the ground for safer landing. So that's why if you go beyond 6 and 7 story high, the fatality rate and also the injury rate for the cats will be lower a little bit. Okay, so that is an interesting thing to know about that. Okay, and that is a statistic published in 1988 in a renowned journal Nature. So researching the cat injury is also research. No, the first thing is the human terminal speed is large. That is the first thing. You cannot land safely if you reach the human terminal speed. Human terminal speed is about 55 to 60 meter per second, which is very fast. That is the first thing. The second thing is that even if you're able to turn your body in the right direction, that speed will obviously kill you. But the cats actually have a much smaller mass than human. So that's why the cats has a much smaller terminal speed. And if you let the cat to relax, it will turn its body to the right position. And also it will scratch out its arm. So at the great height, it will fall like a parachute. Its surface area will be increased. And so it will further decrease its terminal speed. Okay, so that's why it may survive. But for human, if you fall a 6 or 7 story high, you may be about 100% fatal. Yes, there's no chance for you to survive. Now, the angular momentum is actually a vector. Okay, how do we define that vector? How to define the direction of that vector? Well, it's like a talk. Do you remember when we learned about cross product? We use our right hand to define the direction of a cross product. And that is used to define the direction of the moment of force, that is torque, right? Now we define angular momentum, angular velocity within the same way. If a particle now rotates about a certain axis in this sense, then we use our right hand. Our forefinger goes in the direction of that particle, goes along along the linear velocity of that particle, is curved like this. Then the angular momentum or the angular velocity of that particle has a direction defined by the thumb of my right hand. Now that is a definition. That actually means if you say you have the angular velocity in this direction, along the direction of my thumb, the particle actually rotates in the direction of my forefinger. That is a definition. Okay, so we can somehow use a vector, omega or L, that is pointing towards the direction of my thumb to denote a rotation. Okay, to give you the direction of the rotation, and it can be generalized into three-dimensional easily. It does not only include clockwise or anti-clockwise rotation. It can be generalized to an arbitrary axis. For example, you may have a rotation along this axis. You may also have a rotation along that axis. So you generalize the rotation into 3 dimensions, okay, by using vectors. Now, in this example, you have a rotation in opposite direction. So now your thumb is pointing downwards, and that means the rotation direction is reversed, okay? And all the discussion about angular momentum and angular velocity, they should be treated using vectors. Now, this is an interesting demonstration. I'll let you see that demonstration first before talking about what it is. Now, suppose we initially have a person sitting on a chair. The chair is free to rotate. And the person is now holding a bicycle wheel in the horizontal direction. The axis of the bicycle wheel is in the horizontal direction. Now another person comes to spin the wheel. So there's an angular momentum in the horizontal direction, right? Now, but the horizontal direction of the angular momentum doesn't conserve because of the chair. The chair is not free to rotate about this horizontal direction. So there's a torque acting on the person and also the wheel. And so making the angular momentum along the horizontal direction does not conserve. But how about if the person now turn the wheel such that the axis of the wheel is now in vertical direction? Let's see.
Try not spinning. My assistant's going to come and spin this for me. So I have some angular momentum. Now when I rotate it,
now you see his body rotates in the opposite direction.
Stop.
As a wheel, right? When you flip the axis upside down, you can see the person rotate in the opposite direction. Now I see that again. Okay.
Now when I rotate it,
then when I rotate, when the axis of the wheel points upwards,
if I go the other way,
you can see the person rotates in opposite direction. So when you spin it back around, the person also reverses direction, right? Now, why is it so? This phenomenon can only be understood by using the vector concept of angular momentum. Now, initially, because the chair is only free to rotate about the z-axis. The z-axis is the vertical axis. So initially, if the wheel is rotating horizontally with the axis horizontally, but not in the vertical direction, the z component of the total angular momentum is 0, because there is nothing rotating about the vertical axis, right? So the total angular momentum about the z-axis is 0. But when the person now flips his wheel such that the axis of the wheel is pointing to the z direction, to the vertical direction, he creates a moment of angular momentum for the wheel. Let's say the angular momentum of the wheel is now pointing upwards. According to our definition, that means the wheel is now rotating this way. So the angular momentum vector of the wheel is in the upward direction, is in the vertically upward direction. But by conservation of angular momentum, because initially the person and the wheel as a whole does not have a Z component for angular momentum, so that the total angular momentum should conserve, right? So the final angular momentum should also be 0. And since the chair is free to rotate about the Z axis, there is no external torque. So angular momentum about Z direction must be conserved, right? So when the wheel produces an upward angular momentum vector, the person himself must produce a downward angular momentum vector. So that means the person will rotate in the opposite direction to the wheel. If the wheel rotates clockwise, the angular momentum vector upwards, then the person must rotate in the opposite direction, which means he has an angular momentum vector downwards. And the person angular momentum added to the wheel angular momentum is 0. So the total angular momentum is conserved, just like it started initially with 0 total angular momentum. Okay, so that is an interesting trait. Now, in this example, you actually cannot see the torque in action very clearly. The interaction between the complicated interaction between the bicycle wheel and the person is difficult to visualize. It's difficult to handle. But if you believe angular momentum is conserved and angular momentum is actually a vector, that is the conclusion that you can reach. So you see how powerful it is, a conservation law. You don't really need to handle the details about the interaction between the person and the wheel. But somehow by applying the conservation law and treating the angular momentum as a vector, you actually can find how the wheel and the person rotates. They must be rotating in opposite direction with equal but opposite angular momentum. Okay. Now this is Newton's second law with angular momentum. You can find an extension part on Lagrangian equation here in this e-learning. Okay. If you are interested, you can take a look at it. Now we better take